So last time we were into chapter 6, I believe, and we started talking actually about different types of bonding, and we were getting into sort of naming and nomenclature between ionic bonds and covalent bonded items. What I ended up doing with half the class that had a discussion on Monday is I continued talking about naming for a little bit. So what I'm going to do today with everybody right now is we're going to kind of skip ahead here in the notes to bonding. And those that have discussion tonight, we will then continue on with the naming part of it. So we will come back. So those that obviously had lab on Monday, not discussion, we will come back to naming today during discussion. And we're going to pick up with everybody, so at least everybody's sort of on the same page here in terms of what we're talking about. And new for everybody is chemical bonding. So these are obviously in the same notes, the same chapter. This is sort of the back part of the chapter here. And we're going to pick up here on these slides right now. Okay, so let's talk a little bit about chemical bonding. When we actually do make bonds, and there's really two types of bonds that we talked about, I think, the other day there with our naming part of it. There's ionic bond and there's covalent bonds. But when atoms do interact with one another, it is the electrons that really are involved in bonding. So if you think about it, if two atoms sort of come together, really because the electrons are sort of flying on the outside there, they obviously would be the first things that would come in contact with one another. And that's why they are what is involved in bonding. But it's actually special electrons that are really involved in bonding, and they are the valence electrons. And I think we might have talked about it when we were talking about electron configuration. So for example, if we look at something like lithium and write the electron configuration 1s2, 2s1, lithium has basically 2 electrons on the lower energy level. It has 1 electron right here in this orbital on a higher energy level. And it is the electrons on the higher energy level which are really involved in bonding. And those, again, are what are referred to as valence electrons. These guys that are sort of lower in energy, not really involved in bonding. And the reason they're not involved in bonding is they're lower in energy. They're closer to the nucleus, which means the nucleus is pretty much going to hold on to them pretty tightly. The valence electrons are further away from the nucleus. They're not going to be held as tightly, and they're going to be much easier either lost or used for bonding. So these lower ones, which are not involved in bonding, are what are referred to as core electrons. So when we're talking about bonding, which we're going to be talking about here today, obviously, it's really all about those valence electrons. And I think we talked a little bit about last time, or one of those times, about Lewis dot symbols, or sometimes referred to again as electron dot symbols. And basically we use the symbol and we use basically a dot to represent each valence electron. And as we talked about last time, there's really no rule per se, other than really no more than 2 per side. And that maxes out in terms of 8 electrons. I think we also talked about, you could obviously write the electron configuration to figure out how many valence electrons there are, but a much, much easier way to figure out valence electrons is that it equals the group number. So remember that the number of valence electrons equals the group number. And that's why when we look at lithium, it's part of group 1. And it has 1 valence electron, which is that guy right there. If you looked at, excuse me, if you looked at beryllium, 1s2, 2s2, right here is the 2 valence electrons for beryllium, again, group 2. So when you look at the periodic table, again, the group number, they run out of periodic table there. will equal the number of valence electrons. So again, everybody in group 1 has 1, everybody in group 2, 2, 3, 4, 5, 6, 7, and obviously 8 there at the end. Any questions on that there?
Yeah, Professor Ifan, I have a question about those dots.
Yeah.
I don't get those dots.
You don't get the dots where they come from?
Yeah. Can you just
So
give me a recap?
Yeah, so they do come from the valence electrons. So for example, if we look at lithium, which is group 1, it only has 1 valence electron. So you simply just put 1 dot for the 1 valence electron. If you did beryllium, it has 2 valence electrons, you put 2 dots. If you looked at oxygen, which is group 6, it would have 6 valence electrons. And again, you could represent it by 6 dots and so forth. So 1 dot for each of the valence electrons, which are the ones that involve in bonding.
Okay. So pretty much, just for clarity, so those dots, I'm pretty much taking those dots from the group numbers, right?
That's exactly right. Yeah. So exactly what I just said there, that basically the number of valence electrons equals the group number. Okay. So our Lewis dot symbol, as I mentioned earlier, and I think we looked at it last time, again, basically 1 dot for each valence electron. And again, sometimes people just kind of go around and then pair up the dots. But again, really the hard fast rule is really no more than 2 electrons per side. So here in group 1, we have 1 valence electron for everybody. Here in group 2, you see everybody has 2 valence electrons, 3, 4, 5, 6, 7, and then 8. The one exception is obviously helium here. Helium is part of group 8, but it actually only has 2 valence electrons, and that is because helium only has 2 electrons. So one has 2, and both of those electrons are the valence electrons. So because helium really only has a total of 2 electrons, it could only have 2 valence electrons. But everybody else there in group 8, as you can see, neon, argon, krypton, they all will have 8 valence electrons. In terms of the transition metals, which are here, we really don't deal too much with them in terms of bonding and drawing Lewis structures and stuff like that. Again, I might have mentioned, but really what happens with the transition metals is they typically will lose these electrons first, the S's. So sometimes people will say they have 2 valence electrons, but sometimes people will say because they do have all these D ones available to them, they could have upwards of 12 depending on the one you're talking about. So the good news is we don't really deal too much in terms of bonding and drawing things with those transition metals, so you don't have to worry too much about it. But definitely these representative elements here in group 1, 2, 3, 4, 5, 6, 7, 8, we definitely do see those a lot. So these really can help us, as we will see here, describe and show the 2 types of bonding that we come across. One is ionic bonding and one is covalent bonding. Ionic bonding is between a metal and a non-metal, and that's always the case here. And basically what happens in here is there's a transfer of electrons from the metal to the non-metal. That results in this guy becoming positively charged, or a cation. That results in our non-metal becoming negatively charged, or an anion. And what holds that together, the importance is, I think, as we touched upon maybe the last time, in an ionic compound, there's absolutely no sharing of electrons. So there has been a complete transfer of electrons from the metal to the non-metal, which is why they do gain the overall charges of being positive and negative. Covalent bonding, on the other hand, is really between 2 non-metals. And based on those periodic trends, if you remember, we talked a little bit about some periodic trends, because the non-metals are pretty much all located within the same region of the periodic table, they have very similar periodic trends. And what that means is they have very similar properties in terms of what they like to do with their electrons. And that means that they both really like their electrons. They want to hang on to their electrons. They want to actually grab some electrons. So the best that happens when we actually do have two nonmetals that come together is they decide, well, since I want to hold on to my electrons, you want to hold on to your electrons, the best we could do is some sort of sharing of electrons occur here. And as we'll talk about here as we continue on, that sharing of electrons may be equal or unequal sharing of electrons, but there is some type of sharing. And that is different than what happens in an ionic compound. Again, because if you think about sort of an ionic compound, you are basically combining somebody from this side of the periodic table with somebody from this side of the periodic table, and they have very, very different properties in terms of what they want to do with their electrons. Metals, as we talked about, pretty much are like, take my electrons, please. Non-metals are like, I want to accept those electrons, and that's why we get a transfer of electrons. But again, in a covalent compound, we got two nonmetals, which both basically want to hang on to their electrons. So we do get that sort of sharing situation that occurs that we do not see with an ionic bond. And again, an ionic bond, what holds that together is the positive negative attraction between the two charges. That is a very, very super strong attractive force when you have something that's positively charged attracted to something that is negatively charged. So typically speaking, metals will lose electrons, nonmetals will pick up electrons and become negative, and that really is the basis here for bonding. So let's take a look at an example of an ionic compound. And you may be wondering, well, how do I know, just looking at sort of the name here, if it's an ionic compound or not? I know that because lithium is Li, and that is a metal. Fluoride, remember the ID, as we touched upon, I think last time, is for nonmetals on the periodic table. And that combination of metal and nonmetal, you don't need to think about it any more than that. That is going to lead to an ionic bond and an ionic compound. So what happens when we take a lithium ion and we take a fluoride ion and they come together to bond? Well, here's the electron configuration for both of them. And again, lithium, which is group 1, has one valence electron, which is this guy, which means we could draw the Lewis dot symbol for it, which would look something like this. Now, fluorine has 7 electrons here in the second energy level. 2 and 5 make 7. And that is also group 7 on the periodic table, which means that when we do fluorine here, it will have 7 valence electrons to begin. So what's going to happen in this particular case is the lithium is like, take my electron, please. So the nonmetal is like, I want your electron. This is the actual conversation happening. The electron will transfer from lithium to the fluorine. It is at this point, so as we talked about, I think the other day as well, when you look at something on the periodic table, any element that you have on the periodic table, if it is by itself, uncombined, not with anybody else, it does not have a charge. Things only get a charge in this situation here when a metal and a non-metal really come together. The result of this is the lithium has now lost that electron and now has more protons than electrons and becomes positively charged. That electron then ends up over in the fluorine, and the fluorine could accept it because if we look at its electron configuration, it's got an extra spot right there available in the p orbitals. And when it accepts that, now fluorine has more electrons than protons and develops a negative charge. It is this attractive force between the positively charged cation and the negatively charged anion that basically holds that together. We draw these guys for ionic bonding, showing the charges. We also, as you can see here, put one of them in brackets to indicate that there's absolutely no sharing of electrons that are occurring in this situation. First off, any questions on that drawing there? Now, what is happening in terms of electron configuration? When lithium loses that one electron, it loses its valence electron here. And now that lithium no longer has 3 electrons, it actually only has 2 electrons. Ends up with the electron configuration of 1s2. 1s2, if you look on the periodic table, is our good friend helium. What happens to the fluorine is it picks up that electron in the p orbitals. It actually now ends up with 10 electrons and an electron configuration of 1s2, 2s2, 2p6. That is 10 electrons are the same configuration as neon. And this is a really important point in terms of what is happening here in ionic bonding. What we see is both of those elements have now reached the same electron configuration as a noble gas. And that is the basis, this idea right here of the same electron configuration as a noble gas. That is really the basis of all bonding. Ionic bonding, they do that by losing electrons and gaining electrons. As we'll talk about with covalent bonding, they do that by actually sharing the electrons. So this guy again reaches helium's configuration. This guy reaches neon's configuration. And by the way, 2 things that have the same electron configuration, those are what are referred to as being isoelectronic with each other. Isoelectronic means the same electron configuration. So what always happens when we have a representative metal from group 1, group 2, or group 3 that comes together with a non-metal is they all achieve the same electron configuration as a noble gas. The metal goes backwards to the noble gas that comes right before it. The non-metal picks up the electron and goes forward to the noble gas that comes right after it. Any questions on that?
Professor, I have a question. So the number of dots does not necessarily represent the total number of electrons, correct?
That is exactly correct. The total number of dots are only the valence electrons, and we only show those because those really are the ones that are involved in bonding. The core electrons, as we talked about in the case of like lithium, for example, or fluorine here, those are still there, but they're not involved in bonding, so we don't display them in these kind of dot symbols.
Okay, thank you.
You're welcome. Other questions?
Professor, so this is only going to happen when we get to fluorine 9, chlorine 17.
Yeah. So are you talking about this type of situation that's occurring with the transfer of electrons?
Yes.
Yeah, so it will always happen whenever you take a metal and a non-metal that come together. And as you were sort of, I think, naming off there, I remember non-metals are basically above the staircase there, right, on the right. And those guys will always gain electrons. And what happens in usually an ionic compound is they will gain enough electrons to go forward to the noble gas that comes right after them. And then the metals will lose electrons and go backwards to the noble gas that comes right before them.
So it's not going to start happening until right before it hits that last column?
Yeah, so it could be any non-metal. So technically, like nitrogen, for example, phosphorus. You know, any.
Oh,
Yeah, so it's really an ionic bond is just a combination of a non-metal and a metal coming together, basically.
oh, okay. Thank you.
You're welcome. Other,
Professor,
Yeah.
you could only max out at 8 valence, right? Valence electrons. That's it
yeah,
per.
eight in terms of bonding is really kind of the number, and that the reason for that is the noble gases are group 8, right?
Okay.
That's basically means that everybody, as we saw earlier, has 8 valence electrons in group 8, and that's really the goal of what everybody is trying basically to get to.
Okay.
Other questions on that? All right. So as I mentioned before, that is really what an ionic bond is. Really, it's held together by that positive negative attraction. Absolutely no sharing of electrons sort of happening here. I'm not sure I understand the question about what happens when you combine 2 gases. This is, so you can think of this as sort of when 2 individual sort of elements come together. That's sort of what's happening here in this situation.
Wait, so sir, you said that there was no sharing of electrons?
Yeah, there's absolutely no sharing of electrons in an ionic bond. Yep. And again, it is simply like that positive charge and negative charge that's on the cation and the anion. That attractive force between those two is what holds those guys basically together. Again, no sharing of electrons, and that's actually a very, very strong force that holds things together, positive and negative attraction. Yeah.
Well, then, do you know if you go back to the previous slide, because I'm kind of having a hard time understanding that there's no sharing.
You want to go back?
So before the fluoride was in the brackets, the lithium I thought gave that valence electron to chloride, right?
It did, yeah.
So is that considered them sharing, or is that?
It's not sharing. It's been completely transferred over. So when lithium ends up, it no longer has that electron. It's completely gone.
Oh, okay.
Which is why it ends up on the other side with a positive charge and really only 2 electrons left at that point. And the fluorine actually gains the electron and puts it right there in the P subshell. And that's how come it becomes negative. And that's why I was saying earlier that things really don't have charges until sort of this process occurs. That's basically when they kind of gain their charges, when they're, in this particular case, a transfer of electrons. All right, let's take a look at another example. This happens when we put together calcium and oxygen. So it's basically calcium. Again, we know this is going to be an ionic bond because this is a metal. Oxygen is a non-metal. This is ionic. Again, calcium is group number 2. So if we were to draw the Lewis dot symbol, it would be calcium with 2 dots, which represents its valence electrons from group number 2. It also has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And it is these 2 electrons right here in calcium that is the valence electrons. They're represented by those 2 dots. If we take oxygen, oxygen is group 6, which means it has 6 valence electrons. And 1s2, 2s2, 2p4 in this case. And what's going to happen in this case, again, the calcium being a metal, especially when it's around a non-metal like oxygen, is going to go take my electron. So he's going to completely lose 1 electron. And he is actually going to lose a second electron. And that's okay because oxygen actually has room for both of those electrons to go right there. Remember, the p subshell can hold 6 electrons, so it actually has room for it. The result of that is, as we see, calcium has now lost 2 electrons and now has 2 more protons than electrons. And it's at that point, once those electrons have transferred out, that it becomes a positively 2 charge. The oxygen will pick up those 2 electrons and put it into the p subshell. And at that point, the oxygen will now gain those 2 electrons. Not only that, it now has 2 more electrons than protons, and it will pick up a -2 charge. And again, here, there's absolutely no sharing of electrons that are happening. It is the attraction between the +2 and the -2 that's holding that together. What happens in terms of the electron configuration? Calcium loses these 2 electrons, so they're now gone. They've been transferred. That leaves calcium 2, 4, 10, 12, 18 electrons. If you look on the periodic table, number 18 is argon. Oxygen will put those 2 electrons right in there and end up with an electron configuration of 1s2, 2s2, 2p6. And if we count up that is 2, 4, and 10 electrons are the same electron configuration as neon. Once again, here we basically have done what we are trying to do. Calcium, by losing both electrons, ends up at the noble gas configuration, making it very happy and stable. Oxygen, by picking up those 2 electrons, have now moved forward on the periodic table. So if you look where oxygen is, you will see 2 spaces down, neon. So it's able to pick up the electrons and end up with the same electron configuration as neon. Again, that is really the basis of ionic bonding and all bonding, as I mentioned a number of times, for everybody to get to the same electron configuration as the noble gases. Question on that there.
Professor, it always becomes a negative charge when there's more electrons than protons, correct?
It does, because when we think about an atom, it basically has protons that are positive, electrons that are negative, and neutrons that have no charge. So when something gains a charge, it is only the electrons that change. And when they gain electrons and you have more electrons than protons, then you have a negative charge. Vice versa, if you lose electrons, you then have more protons than electrons, and that's why you become positively charged.
Okay. Is there any cases where they stay neutral, or they can't like take any electrons?
No, usually in bonding will involve either one of 2 things. What we're talking about here in ionic bonding, the transfer of electrons, are in covalent bonding, there'll be sharing of electrons. Typically, they will hang on to their electrons if they just, really aren't doing any type of bonding. So
Okay.
if there's some type of bonding happening, there'll usually be one of 2 things, either a transfer of electrons or a sharing of electrons.
Okay.
Other questions?
Professor,
Yes.
on a test, will we be asked to, so then this is basically the answer at the bottom where you have the, the bracket.
Yeah, this would be the correct sort of Lewis structure, if you will, for this ionic compound.
Thank you.
Okay, so
Professor, I'm sorry.
Yeah.
Are we supposed to, like an answer, write that and then write down what the new gas becomes?
If you're asked, are you asking, do we just write the electron configuration?
Yes, the new one.
It depends on the question. If you're asked to, yes. If not, then you would just need to draw the drawing up there.
Okay.
So it kind of would depend on the question, but you do need to kind of understand that that's sort of where these guys will end up, is at a noble gas.
Okay, thank you.
Yep.
I have a question. I'm sorry. Is this always the case where the valence electrons transfer and it gets us to a noble gas, or will we ever come across a situation where it's not just the two, like for example, calcium has the 2 dots, so it's the 2 valence electrons that get transferred over? Is that always the case where whatever the dots is or the valence electron, that's what's always being transferred over?
So the answer is, I'll put it this way. The answer is yes for like the representative elements like group 1, group 2, group 3. Transition metals are a little bit different in terms of how they lose electrons. The good news is we're not going to draw any of those. So for our purposes, I'm going to say yes. It's going to be the dots should transfer if it's a metal and a non-metal. The reality answer is transition metals do sort of operate a little bit different, but we really don't sort of deal too much with them in here at all. So you don't have to worry about them. So I guess the answer would be yes. It should transfer all those things, electrons.
Thank you.
And what I mean by that is the transition metals, when they actually do lose electrons, they do lose those s electrons first, but they don't end up usually at a noble gas configuration. So that's sort of an exception, and we really don't do too much with those. But maybe this is also sort of a question that you might be asking as well. So let me get a little space here to draw. What would happen if we took, say, a calcium, for example, and we actually put it together with our fluorine that we had earlier, which is group 7. Right. Now, remember, our calcium has the same electron configuration to begin with, 1s2, 2s2, 2p6, 3s2, 3p6, and our 4s2. Our fluorine also has 1s2, 2s2, 2p5. So what's going to happen is our calcium here is going to want to get rid of its electron, and we're going to throw it over to this fluorine. Now, we created sort of a problem because, as was mentioned earlier, the magic number here for bonding is 8, which means that this particular fluorine is now going to be filled, which is a problem for calcium because if you look at calcium there on the periodic table, there's potassium and then calcium, and then we have argon, back over here, right? So if calcium only loses 1 electron, it actually ends up with the same electron configuration as potassium, which is not really the goal, right? The goal is for it to get back to a noble gas. So it needs to lose that second electron, but this particular fluorine doesn't have any room for it. And that is why we would actually need not 1 fluorine in this case, but we would need a second fluorine, because the second fluorine will now have room for calcium's second electron. That is now going to allow calcium to lose the second electron and end up back at argon. And the result of that is we will again end up with calcium that has a +2 charge. But we will now end up with a fluorine that gained 1 electron and became -1 charge, and a second fluorine that also gained 1 electron and become -1 charged. The result of this is we have a -1, which is a -2 to balance out the +2 that we see here on calcium. And in this particular case, what that means is if we look at the electron configuration for all 3 of those things, the calcium lost its 2 electrons, became argon. Individually, each of the fluorines put an electron, 1 electron, into the p subshell, and that moved it forward to neon's configuration. And this guy also achieved neon's configuration. So in this particular case, we actually need a couple of fluorines to come together here with the calcium. And again, there's absolutely no sharing of electrons happening here. The attraction between the +2 and the -1s in each of those things is what's basically holding those guys together. Now, this is what we were talking about, and I think we might have got there the other day when we were talking about nomenclatures and writing ionic compounds, the formulas for ionic compound. If you remember, when we write a formula for an ionic compound, the overall charge needs to equal 0, which means when we take a calcium that has a +2 charge and a fluoride that has a -1 charge, we actually do need 2 of those to balance out the charge. And this would be the correct formula for calcium fluoride. And really the basis for why we say when you put a metal and a non-metal together and the positive negative attraction come together, that we want to put it together so we end up with no charge, is because that allows everybody to reach noble gas configuration. The 1 calcium in this example, the 2 fluorines are able to each reach noble gas configuration by gaining and losing electrons. And that's why when we do naming and writing ionic compounds and formulas, we always want to balance out all the positive charge and all the negative charge to equal 0. And we always want to do that in the simplest way possible when we do that to get it to 0. And the basis of that really is the bonding part here. It is to get everybody to reach a noble gas configuration. Question on that there.
Professor, the 2 on below the F, that's indicating that there's 2 fluorides?
There is. So when you write an ionic compound or a formula for anybody, if there's no number written next to it, that means 1, and it goes to the guy to the left. So this 2 would go to the guy to the left, which would be the fluorine. Yeah.
Professor, I have a question.
Yes.
Why would the one where you were at, where it says the Ca2, and then you boxed it into CaF2, why would that not be argon?
Why would
Because in this other example that you gave in the purple on this other side, in the middle, you called it AR and then NE, because it was Ca2 and it's still Ca2 on this other side in the red. It wouldn't change to argon. Argon.
are we talking over here?
Oh, okay. So in the red on the right hand side, you have CaF2.
Right. This
Okay. I'm sorry. Where's your cursor?
right here.
Oh, I think my my box is in the way. Yes, right there.
Okay.
Okay. So the Ca, that wouldn't be brackets AR.
No.
F2?
So we're clear. When I put the brackets here or any of these guys, that is not the name of it or anything like that. That's not the formula of it. That's indicating that it has now achieved the same electron configuration as that noble gas. So it's actually like the electron configuration for that ion. So if you took calcium with a +2 charge and was asked to write the electron configuration for it, it would be 1s2, 2s2, 2p6, 3s2, 3p6, and that's 18. And that would be the electron configuration for calcium with a +2 charge. When you put a bracket in argon, that's like a shorthand electron configuration that indicates that that's the same electron configuration as argon. When
So
we
the
write,
gas doesn't change, right, Professor?
yeah, so the calcium, for example, and the fluorine is not changing. It's just gaining and losing electrons. But what it is doing to itself is it is becoming more like the noble gas in terms of electrons, is becoming exactly the same in terms of electrons as the noble gas. It's not the same thing because argon, right? If we look at just argon by itself, for example, I could find where I could write. If we look at argon, it has 18 protons and 18 electrons, right? And that's argon. If we look at calcium with a +2 charge, calcium with a +2 charge still has to have 20 protons because that's what makes it calcium, because it has the 20 protons. That's its atomic number. but it only has 18 electrons. So what argon and calcium with a +2 charge share in common is they both share the same number of electrons, and they have the same electron configuration, and that makes them sort of stable in terms of bonding. But definitely calcium with a +2 charge is still calcium because it still has 20 protons. And if you remember when we talked about sort of protons, electrons, neutrons, atomic number, and all that kind of stuff, it is the number of protons that determine what element you're talking about. So it doesn't change to argon, but it does achieve the same electron configuration as argon, the same number of electrons, but it definitely still has a different number of protons.
Thank you for the clarification.
Thank you.
Yep. Okay, so that is ionic bonding. And again, if you draw ionic bonding, a couple of key points just to remember, you will get these guys to transfer electrons, metals to the non-metals. And when you do draw these guys in terms of Lewis structures, you do need to include the charges. Typically speaking, you put at least a bracket around maybe the negative guy. Sometimes people put brackets around both of them, and usually those brackets and the charges are drawn in here to indicate that there are no sharing of electrons. Okay, so now that we talked about ionic bonding, let us talk about covalent bonding, which is a little different of a situation. And I think my things went a little awry here. Yes, they did. Okay, let me fix some of those things here for it. Got dots just hanging out. All right. So in a covalent bond, Lewis, which is hence why we call it Lewis structures and all those kind of things, suggested that when we form a chemical bond, it's a result of sharing of electrons. I'm just going to redraw this. This is pretty bad. So for example, if we take a hydrogen, it has one valence electron, and we put it together with another hydrogen that has one valence electron. The difference between sort of this situation and what we were just talking about is what we were talking about before was a metal and a non-metal. Those guys have very different periodic trends, and the metal wants to give away its electron, the non-metal wants to accept it. Here we're actually dealing with two non-metals, and actually two of the same non-metals, which means they actually share the exact same identical trends, which means because they're both non-metals, neither one of these hydrogens want to give away their electrons and let it get transferred. So what's going to happen in this case is the best they're going to agree upon is we're going to share these electrons. And the result of that is we end up with hydrogen that is now sharing those two electrons. And when we count up the electrons for the hydrogen on the left, he gets to count both of those electrons that are being shared between them. And if we count up the electrons for the hydrogen on the right, he also gets to count the two electrons that are being shared between them. And because they are electrons, there is going to be an attraction of those negatively charged electrons to one of the hydrogens, and some attraction of those negatively charged electrons to the other hydrogen's nucleus, which is positively charged. And it's that kind of mutual attraction that kind of locks those electrons in place, if you want to imagine, between these two guys. And that forms a covalent bond, which we have sharing of electrons. You could also represent this sharing of electrons by a line. The line represents two dots, or a pair of electrons. This is what is referred to as a covalent bond. And in this particular case, because they are both hydrogen, we would expect those electrons to be shared equally. This is an equal sharing that's going to be happening here. How do we know it's going to be equal? Because they're both hydrogen, which means you could think of it like a tug of war, like pulling on a rope. You put somebody on one side and like their exact duplicate twin robot on the other side. They're both going to pull that rope equally. And you got like the little flag. It's not going to go anywhere because they're both pulling pretty much equally. And those electrons will be shared equally. This type of bond represents a covalent bond, which means that they are being shared. And when we have equal sharing of electrons, this is what is referred to as a nonpolar covalent bond. And basically, nonpolar means equal sharing. Most people just shorthand it and call it a nonpolar bond. What makes hydrogen okay with this? Well, if we look at the periodic table and we find hydrogen, which is number 1, if we go past hydrogen to the next noble gas, that is number 2, which is helium. And in this particular case, by sharing electrons, the hydrogen on the left has 2 electrons, hydrogen on the right has 2 electrons. They have both here, unlike in an ionic bond where the electrons were completely transferred, here in this particular case, they actually achieve noble gas configuration by sharing electrons. And that's the deal with covalent bonds. They actually share electrons to reach the noble gas configuration. Any questions on that there? Also, a really important thing in terms of bonding, hydrogen, only 2 electrons. Everybody else 8. Hydrogen only needs 2 because, as you can see here, it just needs to get to helium in terms of getting to a noble gas configuration, and hydrogen should only have 2 electrons. So you should never put dots all the way around hydrogen. It's definitely wrong. You should never double bond or triple bond hydrogen. It is definitely wrong as well. So hydrogen only needs to reach basically the configuration of helium to be happy and basically share those electrons and reach that noble gas configuration. Yeah, so the question is, equal sharing is a nonpolar bond. Yes, that's exactly it. It really is a covalent bond because the sharing aspect of it makes it a covalent bond, but most people call it a nonpolar bond. The official right name, I guess, is a nonpolar covalent bond. But like I said, most people just kind of leave the covalent part out and just say nonpolar bond. But definitely nonpolar means equal sharing of electrons when we're talking about bonding. Now, what happens if we look at something like fluorine, for example? That is 2 fluorines together. They again are both group 7, which means each of the fluorines here will have 7 electrons. And again, in this situation, because they're both fluorine, they're definitely going to have the identical type of periodic trends, which means neither one of them are going to give up their electrons in this case. Again, we're going to get a situation where these 2 electrons here are going to be shared between the 2 fluorines. The result of that is we end up with a fluorine over here on the left, bonded now with those 2 electrons in the middle to the fluorine on the right. And just like in an ionic bond, again, in this case, though, no sharing of, no transfer of electrons, but through sharing of electrons, the electrons in the middle count for the guy on the left, which gives him 2, 4, 6, 8 electrons. The fluorine on the right also gets to count those guys in the middle, giving it 2, 4, 6, 8 electrons. And again, 8 valence electrons on the periodic table now allows each of these fluorines to reach noble gas configuration and be very happy, and a good bond is formed. Again, you could show it with dots, or you could show those electrons with a line that represents the sharing of electrons. Either one is perfectly fine. Personally, I go with the line, but if you want to do dots for everything, you can. There's nothing really wrong with it. This also would be considered a nonpolar bond. We would expect that these electrons to be shared equally between the 2 fluorines, Again, if you just kind of take the tug of war rope example, you got basically the same person on both sides of the rope pulling. That rope basically is not going to go anywhere because they're pulling equal and sort of opposite of each other. Any questions on that there?
So this would have the same configuration as the neon, right?
It would in this case. So fluorine, each of the fluorines in this case would go forward to neon.
Yeah,
And they
okay.
do that basically because they both basically started with 7. And they're sharing that electron, which counts for both of them, which means they both kind of move forward to neon's configuration.
Oh, okay, cool.
Other questions? Now, when we look at this sort of Lewis structure here, there's some different types of electrons that we sometimes talk about, and it's going to be important a little bit later on when we talk about geometry and so forth. All of the electrons sort of on the outside here represented with dots in this particular case. All these guys. They are not involved in any type of bonding. And we know that because there's no other element on the other side of those dots. And these are what are referred to as non-bonding electrons. Most people call it non-bonding electrons these days. If you're old like me, you might call it still lone pairs. So if you hear me say lone pairs, it's the same thing as non-bonding electrons. There are basically electrons that are not involved in any type of bond formation. That obviously leaves us the other type of electrons that in this particular case is represented by the line here. Those electrons there are involved in bonding, and they have a very creative name. They are what are referred to as bonding electrons because they are involved in bonding. So when you draw Lewis structures, you always want to make sure that you draw both the bonding electrons and the non-bonding electrons, and they should be represented in your picture. Oops. Now, a Lewis structure, again, we use them to represent covalent bonding, representing sharing of electrons, again, with either dots or lines. And as I think was an earlier question, the answer is, yeah, it is just the valence electrons that are shown in these pictures because they are the ones that are involved in bonding. Again, all these guys have other electrons, which are those core electrons, which are closer to the nucleus, held a lot tighter and not really involved in bonding. So you definitely have other electrons there, but these Lewis structures are only concerned with, what is involved in bonding. If we look at the Lewis structure here for water, for example, water actually shares some electrons. The oxygen in water shares with both hydrogens. So as you can see on the bottom there, the 2 electrons being shared there for our hydrogens, and then the oxygen sharing those electrons on the other side. And again, what this allows us to see is the oxygen hits the magic number of 8. Each of the hydrogens hit the magic number of 2 for hydrogen. And everybody again hits the noble gas configuration and is very happy. And really, again, the purpose of sort of bonding here. That brings up, as you can see, are a couple of numbers which are really important in terms of bonding. 8 is the big number in bonding. 8 is sometimes referred to as the Octet Rule. The Octet Rule basically means that everybody will continue to make bonds until it has 8 valence electrons around it. And that is obviously everybody except for hydrogen, which will only need 2 electrons, as we talked about a little bit earlier. It only needs to get to helium. Hydrogen is sometimes referred to as the duet rule because it only needs 2 electrons. So basically, when you start drawing Lewis structures, pretty much hydrogen should always be on the outside, pretty much one line to it, which would represent 2 electrons, and that's it. If you ever find yourself doing like some double bonding to hydrogen, it's wrong, cross it out. If you're doing like a triple bond to hydrogen, it's wrong, cross it out. If you're doing hydrogen and you're putting dots all the way around, save me the trouble, mark it off yourself there. It is wrong. Hydrogen pretty much should look just like this, or it should look like this. and that's it. It should never have any more than 2 electrons. And I can't tell you how often people screw that up. They just keep on stacking on electrons to hydrogen. And before you know it, hydrogen's got like dots all over it and things like that. Now, to reach the octet rule, to make everybody happy, sometimes that requires just a single bond, as we see here with fluorine. Just requires a single bond, which basically can be represented by one line or basically a pair of electrons or 2 dots. There are certain cases where, you just can't get that octet rule met with single bonds. So sometimes we could fix that by making a double bond. And we actually see that in CO2 here. The carbon makes a double bond represented by 2 lines, are 4 dots or 2 pairs of electrons, and actually makes a double bond on both sides. And that gives the carbon here 2, 4, 6, 8, gives the oxygen on the right 2, 4, 6, 8, oxygen on the left 2, 4, 6, 8. Everybody gets to 8 electrons. Everybody is happy with the number of valence electrons that it has. Now, sometimes you need to go even further than a double bond, and that is a triple bond. Here's a couple of examples of triple bonds that are sort of needed. Nitrogen, for example, needs to make a triple bond represented by 3 lines, are again 3 pairs of dots, which is 6 total electrons, makes a triple bond. In the case of the nitrogen on the right here, it's got 6 electrons in the middle, 2 more on the outside is 8. Nitrogen on the left, 6 electrons in the middle, 2 more on the outside, it's 8. Again, by making that triple bond, it allows it to reach the octet rule and then be really happy. We see down here, carbon actually making a triple bond, again, sharing 6 electrons between each carbon, and 2 with the hydrogen gives it 8. And same thing with the carbon on the left, 6 in the middle, 2 on the left, gives it 8. We also see here our important rule for hydrogen still only has 2 electrons. So again, really important to remember, hydrogen only 2 electrons. So to represent bonding electrons, you can either use lines or dots. And again, if you're doing a triple bond, it should be some type of stacked dots. If you're using dots, you can't just kind of go straight, dots all the way around. That's not a triple bond. So either lines or dots, and it's your preference. Like I said before, I personally will use lines to represent bonding electrons, but if you would like to use dots, it technically is not wrong. So how do we know when we are sharing electrons between these nonmetals, if they will be shared equally or unequally? It really is the electronegativity that helps us determine if these electrons are going to be shared equally or unequally. What is electronegativity? We might have talked about it, but just in case, we'll see it in just a second, I think again. Electronegativity is the ability of an atom to bring electrons towards itself. When you look on the periodic table, electronegativity increases as you go up and to the right, decreases as you go down. Our good friend fluorine is the most electronegative element you can have. So earlier when we were talking about the hydrogen bond and those electrons that are being shared between the 2 hydrogens, we would expect them to be shared equally because they're both hydrogen, or even with our fluorine, we would expect them to be shared equally between them. But what happens when we have this type of thing? As I mentioned before, this represents a nonpolar bond. But what would happen if we swap out one of the fluorines for something like hydrogen? So if we take hydrogen and bond it to fluorine, these are now two different elements. And as I just mentioned a second ago, fluorine is the most electronegative element there is, which means as they are sharing these electrons, and if you think about sort of our pulling on a rope example, in this particular case, we have fluorine, which really wants the electrons. So it's going to basically pull those electrons towards the fluorine. The hydrogen is going to kind of hang on a little bit, but most of the electrons are going to find their way to the fluorine. So like if you were doing the tug of war and you had, you know, a small person on one side and like 4 people on the other side pulling, obviously the rope's going to pull towards the side with the 4 people because it's pulling those electrons a lot more in this particular case. The result of that is we're no longer going to have these electrons being shared equally with one another. It's going to create what is referred to as a polar covalent bond, or sometimes just referred to as a polar bond. But what is really happening when we sort of analyze between the hydrogen and the fluorine? Well, if all of the electrons are kind of being pulled over here, fluorine will now become more negative than hydrogen because hydrogen, all its electrons are basically going towards fluorine. And it creates what is referred to as a partially negative charge on the fluorine. That's a delta symbol. Delta negative, partially negative charge. And hydrogen becomes a partially positive charge on the hydrogen. It can also be represented with an arrow that we'll see a lot. And this is what is sometimes referred to as a bond dipole arrow. It points to the side that's more negative. And the part that makes like a plus on the back end is to the side that is more positive in a bond. And this represents a polar covalent bond. Now, you may be asking, you know, again, these are what are referred to as partially positive, partially negative. Why are they partially positive and partially negatively charged? The answer is they are still sharing the electrons. So even though the fluorine is pulling the rope, right? Like in our tug of war example, maybe you've seen it, right? They pull the rope. That poor person that's all by themselves on the other side, still hanging on to the rope, right? And they get pulled like into the mud, but they're still hanging on to the rope. And that's sort of the situation here with the hydrogen. Although the electrons are pretty much all vacationing over there with the fluorine, hydrogen is still able to hang on to those electrons a little bit. And there's some aspect of sharing that's still going on in this case. And that is why we get a partially positive charge and a partially negative charge. And that is different than when we take a sodium ion or a sodium and put it with a chlorine. In this particular case, the sodium just gives away its electron and it fully transfers the electron. And that's why sodium becomes fully positively one charge. The chlorine accepts the complete electron, and why it becomes negatively one charge, full charges in an ionic bond. In this covalent bond, the hydrogen is still barely hanging on, and there's still some aspect of sharing. So we don't actually get the complete transfer of those electrons from one guy to the next, like we saw in the ionic bond. Question on that there. So that's basically what this smear shows. The pink is sort of where the electron density. And again, most of the electrons hanging out near the fluorine because it's attracting those electrons to really move closer to the fluorine, creating that partially negative charge on the fluorine side, partially positive charge on the hydrogen side. So what is a polar bond? It is just that, like a nonpolar bond is equal sharing of electrons. A polar bond is unequal sharing of electrons. Any questions on that there?
Professor, so when we write the formula or the answers, we have to write the delta sign as well?
I'm sorry, say it one more time. I missed the first part.
If
of
we
it.
have to write an answer, do we have to write like the delta positive charge, the delta negative charge?
If you were to, so if you were just asked to draw the Lewis structure for this guy, you really would have to really draw this. If you were asked to include like the dipole arrow or the partial charges, then you would have to do that. But in most cases, you probably would just be drawing the Lewis structure. But this sort of partially positive and partially negative charge is really important for other sort of interactions we'll talk about down the road.
Okay.
Other questions? All right, so as I mentioned before, this unequal sharing of electrons basically represents a polar covalent bond. And at this point, we sort of talked about 3 different types of bonding. So just to illustrate them again, at one extreme, you have an ionic bond, always between a metal and a non-metal. Always in this situation, the metal is going to completely transfer electrons. The result of that, as we talked about, is a cation that's positively charged, anion that's negatively charged. Again, no sharing of electrons here, but it's that positive negative attraction that holds it together. An example would be something like sodium chloride, which is a metal and non-metal together. On the other end of the extreme, we have a nonpolar bond, or again, a nonpolar covalent bond. That is between 2 nonmetals. There is sharing of electrons. And more importantly, there is equal sharing of electrons. An example will be a couple we saw, H2, F2. Those are again examples of that. And sort of in the middle is a polar covalent bond, or just a polar bond. Also between 2 nonmetals. Also sharing of electrons. But here, unequal sharing of electrons. Like our example right here, HF. So again, one end of the stream, like nonpolar, we got perfect equal sharing of electrons. On the other end of the extreme, we have absolutely no sharing of electrons with ionic bond. They have been transferred completely from the metal to the non-metal, which is why the metal then becomes fully positively charged and the non-metal becomes fully negatively charged. And in the middle, we have sort of, well, not equal sharing of electrons, but not so unequal sharing of electrons that they have completely transferred. There's some aspect of sharing occurring here with a polar bond, but the sharing definitely is not equal. And there is degrees of not being equal sharing. Some really are not equal sharing, like HF actually is very, very unequal sharing. And there's some unequal sharing that's, pretty close to being, pretty close to being equal sharing, but just a little bit unequal in terms of the sharing. Any questions about those different types of bonds? Okay. So how do we determine if we're going to deal with sort of a ionic bond, a polar bond, a non-polar bond? It really is the electronegativity that helps us determine that. Electronegativity, as I mentioned before, again, is the ability really of an atom to sort of bring electrons towards itself. Fluorine is the most electronegative atom you could have. It has a really high electron affinity, which means it likes electrons. It has a really high ionization energy, which means it takes a lot of energy to try to remove electrons, and it typically doesn't happen for something like fluorine. Sodium, on the other hand, has low electron affinity, which means it doesn't really like electrons. And it has low ionization energy, which means it doesn't take a lot of convincing for sodium to go take my electron. So a guy by the name of Pauling came up with some values for electronegativity. And as we talked about earlier, it increases as you go up to the right on the periodic table, decreases as you go down and left to the periodic table. But Pauling came up with an idea of values of 0 to 4. 4 is the most electronegative atom. 0, not so much. So what we do to help us determine sort of is a bond polar, nonpolar, or ionic is we take what is referred to as delta En, and that is sometimes referred to as the difference in electronegativity values, basically. So basically you go to the chart, which we'll take a look at here in just a second, and you take the two elements, you take their two values for electronegativity, and you simply subtract them, large number minus small number. And if you subtract them and the difference in electronegativity is anywhere from 0 to 0.4, that is considered a nonpolar covalent bond. If you do the subtraction and it's above 0.4, like 0.5, to below 2, that is some type of polar covalent bond. If you're typically above 2 in terms of the difference, that is usually an ionic bond. The truth is you don't really need to use the electronegativity values for an ionic bond because as soon as you see it's a metal and a non-metal together, you will know it's a ionic bond. You don't really need it, but you can use them. It's not 100% perfect, the values here, but it works pretty well. So here's a table of electronegativity values. I think I got a bigger one here somewhere. We'll use this one here. There's a bigger table of all the electronegativity values. And we do see a couple of things. We do see as we go to the right, it increases with fluorine being the most. As we go down and to the left there, it decreases with francium over here being pretty low. And let's talk about a couple of the examples that we saw. We had originally a bond between sodium and chloride to make sodium chloride. We could look on the table here for sodium. It is 0.9. Chlorine is 3. So when we do the difference in electronegativity values, that is 3 minus 0.9. That is a difference of 2.1. Remember that when you have a difference of above 2, typically speaking, that means that this bond is ionic. Again, you really don't need these numbers because if you see it as a metal and a non-metal, you know it's ionic. If we look at our fluorine, for example, fluorine on the periodic table here, on this electronegativity table has a value of 4. The other fluorine has a value of 4, which means when we do the difference in electronegativity, we end up with 4 minus 4, which is 0. And if you remember on that scale I wrote, 0 to 0.4 is a nonpolar bond, which is what we talked about earlier. That is how we kind of know this is going to be a nonpolar bond. If we look at our good friend H and F, H is electronegativity value of 2.1. Fluorine has an electronegativity value of 4. The difference in electronegativity value is 4 minus 2.1. No, I'm going to call that 1.9 difference. Again, if we go back and look at our scale here, above 0.4 but below 2 is a polar bond. Now, this is what we were talking about earlier. This is a polar bond. And you know what? That is super unequal sharing, as obviously it's almost 2, which is like where we start to see electrons actually start to transfer. But it's actually 1.9, so it's still hanging on. Again, that hydrogen, as we talked about there. Any questions on that there?
Professor, why if the like for example for sodium and chloride, why do you subtract the 9 from the 3, not the 3 from the 0.9?
Truthfully, when you're doing this and using these electronegativity values, really the purpose here is you just want a positive number. So you could just take
Oh,
the
okay.
bigger number minus the smaller number. It's really the number difference that's important here. And if that number difference, again, can just make it positive, or take the larger minus the smaller. But again, it's that difference in those numbers is really what you're looking at to help you decide if it's polar, ionic, or non-polar. Other questions? Okay, so why don't you try some here? Let's say we had a bond between, let's do potassium and oxygen. Let us do carbon and nitrogen. Let us do oxygen and sulfur. Let us do carbon and hydrogen. And lastly, let us do nitrogen and chlorine. So use this table, calculate the difference in electronegativity, and then determine is the bond ionic, polar, or non-polar. So take a couple of minutes here, calculate the difference in electronegativity values of each of these, and determine what type of bond are we dealing with. Take a look to see how we're doing. So again, we simply just want to go to the table here. We could find potassium is 0.8. That's a very bad, try that again. There we go. Oxygen there is 3.5. So again, if we're going to calculate the difference in electronegativity, simply we're just going to take the bigger number minus the smaller number there. Calculator would be great. So that's like 2.7 perhaps. Yeah, that's the difference there, I think. And that 2.7 is definitely above 2, which would make it an ionic bond in this case. Again, we really didn't need these numbers, just to reassure you in case you don't have the numbers. We could see that K is a metal, O is a non-metal, so we would probably safely assume that this should definitely be an ionic bond, even without the difference in electronegativity. Any questions on that one there? Carbon is 2.5, nitrogen is 3. Again, if we do a little difference there, that is 3 minus 2.5. That is going to give us a 0.5 difference. And remember, above 0.4, which is basically 0.5, that is considered a polar bond. Where are the electrons going to be in this case? Well, the electrons are going to be heading towards the nitrogen in this case. It's going to be more electronegative. It's going to pull the electrons. That means in this bond, the nitrogen would be partially negative. The carbon would be partially positive because of that unequal sharing. Because it's a polar covalent bond, it's still going to be sharing the electrons. And again, that's why we have the partially charged here. Oxygen is 3.5. Sulfur is 2.5. Again, if we do a little difference in electronegativity, 3.5 minus 2.5 going to give us a difference of 1. 1 is obviously above 0.4, but below 2. This also would be a polar bond. Here, the electrons would be heading towards the oxygen in this case, it being more electronegative, partially negative on the oxygen, partially positive on the sulfur. Any questions on that one there? Carbon and hydrogen. Carbon is 2.5. Hydrogen is 2.1. So the difference in electronegativity is 2.5 minus 2.1. That is 0.4. 0.4 is our cutoff for a non-polar bond. So this actually would be a non-polar bond. The difference is 0.4, and again, 0 to 0.4 is considered non-polar. And really this bond right here, this carbon-hydrogen bond, is really the reason for that cutoff, because the basis of organic chemistry, as we will talk about later in the semester, is bonds between carbons and hydrogens, carbons and carbons. It's all this non-polar bonds that occur, and that's really why the cutoff is 0.4. So the carbon-hydrogen bond would be a non-polar bond. Nitrogen and chlorine. Nitrogen would be 3. Chlorine would be 3. Difference in electronegativity here, 3 minus 3 gives me 0. That is a difference of 0. That is what is referred to as a non-polar bond. Couple of things about that. When you do have a difference of 0, so when you do have a electronegativity value difference of 0, it definitely is what is referred to as a non-polar bond. It definitely is a non-polar covalent bond, really. But sometimes books and people, when you have that like perfect, and this is basically perfect equal sharing of electrons because the difference is 0. Sometimes people will also refer to this as a pure covalent bond. If you ever hear somebody say pure covalent bond, what that basically means is you have a bond that is perfectly equal in terms of sharing. There's absolutely no difference in the sharing like we had with H2 or F2, and we got perfect equal sharing of electrons. A pure covalent bond is still a non-polar bond, but sometimes people will make that distinction because of that perfect equal sharing of electrons. First off, any questions on how to use it?
Professor, can you go back to the slide where it gives us the specific numbers on how to determine whether it's a ionic bond, polar bond?
Yeah,
the numbers?
I'll just write it right here on this
All
slide.
right, please. Thank you.
So basically, when you do the difference in electronegativity, anywhere from 0 to 0.4 is considered a non-polar bond. Anywhere from really above 0.4, which is really like 0.5, to below 2 is considered a polar bond. And anywhere typically above 2 is considered ionic. And again, there are some exceptions, even with ionic, that you can have a difference that is not really above 2 and still be ionic. So really with ionic, and what we'll finish up here on talking is this.
I'm sorry, above 2 is what?
Above 2 is ionic bond.
Ionic. Okay, thank you.
Now, really, there are certain cases where you don't really need the actual values here. So for example, one case is what we just were talking about. If you know it's a metal and non-metal, you don't really need the numbers. It's a safe bet to say it's an ionic bond. There's going to be a transfer of electrons. There's going to be something that becomes positively charged, something that becomes negatively charged. You don't actually need the numbers if you are dealing with 2 elements that are in the same row, like we were with this guy. We actually didn't even need the numbers to make a pretty safe bet because they are right there in the same period. And we see that nitrogen is further to the right than carbon. And because they're in the same period, we know it's going to be unequal sharing of electrons. We know nitrogen is going to be more electronegative than carbon because, again, as it goes up and to the right, it increases. So without even the numbers, we could make a safe bet that this bond here would be polar. We could also do the same thing with this guy. Oxygen and sulfur are in the same group. And we know that oxygen is further up on the periodic table, which means it should be more electronegative than sulfur. And it's a pretty safe bet that it's going to be polar. So there's a lot of situations that you don't necessarily need the actual numbers to make a fairly educated guess. And those are definitely cases where you're in the same row, the same group. And again, knowing the general trend of up and to the right, it increases, down and to the left, it decreases, you can make a fairly good sort of situation. This last one that we did here is a prime example of you definitely can have two different elements and still have a nonpolar bond. And the reason for that is when we look at nitrogen, which is right here, it is further up on the periodic table than chlorine, but chlorine is further to the right. So they actually cancel each other out. And that relationship is what is known as the diagonal relationship that you sometimes see on the periodic table. One is further up, one is further to the right, and they end up canceling out their differences. We see that here with carbon and sulfur. One is further up, one is further to the right, they cancel each other out. So we see that in several places on the periodic table where you have sort of that diagonal relationship, as we see here, where again, one is further up, one's further to the right, and they sort of cancel out their contributions. We even see it coming this way as well. So, you know, there's a lot of cases where you could just simply look at the periodic table, use the general trend, and really be able to figure out sort of what is going on without even the numbers. Obviously, if you need the numbers, they would be provided for you. You just obviously need to know what to do with them. Any questions on that there?